Welcome, everyone. Antoine is going to be telling us about C2 co-algebras and vertex co-algebra duality. Take it away, Antoine.
Okay, so thank you very much for having me. It's good to be back after some time. So my talk today will be about C2 co-algebra and some type of vertex algebra duality. And it's it's a joint work with Zhongzhu Lin. And so here you have the archive link. So if you are interested in more details, because I won't be able to provide details on everything during this talk, you can check the paper on the archive. So first, short outline of the talk. In the first section, so I will talk about the motivation and the context of the talk, and then I will lay out the settings and the definitions so that we know what type of objects we consider. Then in the second part, I will give the definition of the vertex algebra and vertex coalgebra I'm looking at, and try to describe some of their properties. In the third section, we will go to the C2, let's say C2 setting coming from the section 2. And I will then give some properties and explain the duality that appears in the title. And finally, in the fourth section, I will give some perspectives on this work and the type of the remaining open questions that I'm interested to look at. So first, for the motivation and context. So as most of you, I'm sure, know, vertex algebra can be thought of generalization of either rings or algebras, depending on which mode you want to look at. And the setting we are interested in is to formulate vertex algebras within a closed monoidal category and to try to kind of work as generally as we can to really understand what are the main components of what makes a vertex algebra. And the purpose of this is to construct resolutions of vertex algebra modules. So as you have a ring and a module, you can construct resolution of this module. So you have a long exact sequence of module for the ring you consider. And we want to do some type of similar construction for vertex algebras. And the second point is, as we will describe in this talk, we want to study a type of duality. So of course, it's when it exists, because we will need to satisfy some condition for the existence, associated to those vertex algebra within the monoidal category and the subsequent C2, so algebra and coalgebra that we will define. And as you know, if you have a coalgebra, the dual of it is always an algebra. So you can always reverse the direction of your morphism and obtain a product on your dual. But the converse is not always true. So you have some type of disparity on when so a coproduct will always lead to a product when you dualize the maps, but the reverse is not true. And so what happens when instead of just a product or a coproduct, you look at the infinitely many products you have for your vertex algebra? Do you have some type of duality? In which direction are you always allowed to go? Do you have some obstructions? And so we want to look at these questions. So these are for the two main motivations of why we looked at the object I will describe in this talk. So to set the context, if you work in symmetric rigid tensor category, so tensor category, you have a tensor product. Rigid is, sorry, you have a notion of dual elements. So you have evaluation and co-evaluation map, and you have a nice dual structure. And symmetric, you have a braiding where when you do the braiding twice, it's isomorphic to just the identity. And so if you are in such a category, we know that the duality, so the dual functor, gives an isomorphism between the category of algebra and the category of co-algebras. And then basically you don't have anything to do because everything is one-to-one. So the idea is we want to work in a non-rigid category so that we don't have this isomorphism, and then the let's say the algebra and co-algebra realm will be a bit different. We won't have this one-to-one correspondence. So to start giving the notations, because we rely on lots of notations for this talk. So we will work with gamma will always be an abelian group, and K will always be a field. And so if you work with so a gamma graded K vector space, you can see this vector space as a K gamma comodule. So K gamma is a group algebra of your abelian group. And the comodule structure, so it's a map from V to V times the group algebra. So this is an element of V, and this is an element of K gamma. Here, the decomposition is that V gamma corresponds to the decomposition of V according to your gradation. So here the sum is finite, so this sum here is finite, and there's no issue. And so you notice that this is the right comodal structure, so the coalgebra appears on the right side. And so the naming of these spaces, so this comodule, in the literature they are called rational G gamma module, where G gamma is the group, so the spectrum of your group algebra. So I put rational in parentheses because we will kind of abuse notation and only talk about G gamma module. And so instead of saying always rational G gamma module, we will just omit the rational, but remember that it's always there. So you can think of these vector spaces as comodule, and then you can also see them as module. So it's not obvious as to what is the action of this G gamma, but we can give an explicit description. And so G apply to an element V gamma inside the gamma summand. It will be a kind of diagonal action where the eigenvalue will be gamma of G, where your element gamma is seen. So an element gamma is an element in your group algebra, but you can see it as a homomorphism between G gamma and Gm. So you can kind of play with the notation, and your space, your gamma graded vector space, you can see it either as just a vector space with a gradation, or as a comodule, or as a module for G gamma. So these are the type of spaces that we will give additional structure, and so vertex algebra, vertex coalgebra, and so on. So these are the, let's say, basic building blocks of the subsequent constructions. And yes, to fix the notation, so the category of, so again, rational G gamma module, we will write it as G mod. So these will be the main category we work with. So this category, G gamma mod, it is a symmetric monoidal category. So we have a tensor product, we have a braiding, and so the braiding is the usual one where you just permute the terms in the tensor product. And it is also a closed category. So meaning of closed is you have what's called an internal Hom space. So this means that for any two objects VW in G gamma mod, you will have another element. So we will write it this curly Hom also in G gamma mod. Yeah, so here I will also abuse notation. So this means that V and W are objects in the category. So I will just say it belongs to the category, but always it's assumed that it's objects in this category. So for two objects, you have another object where you have this isomorphism between vector spaces. So basically, if you have a homomorphism of G gamma module between the tensor product and W, you can move V on the other side. of the Hom. So instead of starting of being the codomain, it goes into the domain. And you have the image space becomes this Hom of VW. So this is the usual duality you have with vector spaces, but kind of more formalized. So this is the meaning of a closed category, closed monoidal category. Because this is an element in G gamma mod, so it needs to be a graded gamma module. So a graded vector space, sorry. And so the definition is that the space of degree, so of gamma degree, small gamma, is given by all the K homomorphism of degree gamma. So meaning that you go from an element, a space of degree gamma prime, and the degree jumps by gamma. And so you have this jump of gamma on each summand. And you can either see this as an infinite product, so infinite if gamma is infinite, but as a product over gamma. But you can also write it as just the G gamma homomorphism. So you preserve the structure of gamma graded module, but you kind of shift the degree of V by this gamma. And so this Hom G gamma is all the, what's the one? Homogeneous homomorphisms. And because you shifted by gamma, it means that you go from V to W where you shift by this gamma. And so you take the sum over all the gammas and it gives you the graded structure. But as I mentioned in the previous slide, we want to work in something that is not rigid. So you don't always have this nice duality with evaluation and co-evaluation map. And it is the case that for this G gamma module, it is not rigid. And you can see if you work with, if everything is finite dimensional, you will have this evaluation and co-evaluation map. But for infinite dimensional spaces, you won't have the co-evaluation map. This will fail, and then the rigidity of the category will disappear. So then this G gamma module is a good candidate for our study because you have all the nice properties, so symmetric, monoidal, you have a nice tensor product, you have the Hom space, which will be a key component. But because it's not rigid, everything is not as obvious as described in the previous slide where you have the one-to-one between algebra and co-algebra. So this G gamma mod will be the setting we look at. Then if you have an element in G gamma mod, so an object, it's dual, so you look at just the linear maps from V to the field K, is not necessarily an element in G gamma mod. So the gradation might not be preserved by looking at the dual as a whole on the space, because you might have infinitely many components. And so the duality might not, let's say, pass through all the summand of the gradation. And this is due to the fact that the Hom, so on the left side, will turn the direct sum into a direct product. And so you won't get a graded space. So the next, let's say, best candidate to play the role of this dual will be the restricted dual. And so the restricted dual, so we will note that V prime will be the internal Hom between V and K. So this, based on the previous slide, we know it's an element of the category. It's an object. It's a G gamma module. And we can verify, if we compute, that it's the same thing as all the sum of the K maps between V minus gamma and K. So this is basically the sum of the dual of each component, where the part of degree gamma corresponds to the dual of V minus gamma. So you have a sign change when you go to the dual. But the important part is that this is an element in G gamma, whereas this might not be, this V star. And so we stay in our category. Then to fix also a notation, we will say that V is Harish-Chandra if all the components V gamma are finite dimensionals. So we allow for infinitely many components. This is allowed. But for it to be Harish-Chandra, these possibly infinitely many components all need to be finite dimensional. And this is equivalent to saying that we want V to be isomorphic to the dual of the dual. So the restricted dual of the restricted dual. So when I will say dual now, it's always assumed that it's the restricted dual that plays the role. And so these Harish-Chandra module will satisfy this identity, which will become very convenient later on. And also to fix the notation, we have a map between so V prime times U prime into, so notice that the dual of you switch the order between U and V. And so this is given by this bracket where if you have F and G on the left, F will take V, so you have F of V here, and you have G of U. So you don't do it term by term, but you have kind of a change in the order. So the utmost left will take the utmost right, and the inner left will take the inner right. And so this is the correspondence we will use to go from dual of tensor product to tensor product of dual. And this map, it's just a map, it's a homomorphism of G gamma module, but it's not an isomorphism in general. So you can go from one side, but to go in the other direction, you need extra conditions that we will not always need. Sometimes we might use them, but it's we don't always need this to be an isomorphism. It's the setting is more general. Now we go to the loop algebra. So if I'm sure you're familiar with vertex algebra, and the loop algebra is always lurking somewhere. So we need a good setting for the loop algebra in our space. So we fix gamma 0 an element in gamma. And we define the loop algebra, so we write it k of t minus 1, where k of tn, so the space k of tn, is seen as, so this kn gamma 0, where this is basically k, but centered in degree n gamma 0. So k, usually you see it centered in just 0, and here you kind of move it along the degrees according to this, to the degree n. So this is, of course, a G gamma module because every component is just one dimensional, so you have a nice gradation. And because you have only polynomial, you have finitely many components, so there's no problem. And then we have the identification we often use for vertex algebra, is that if you look at so the K homomorphism between the loop algebra and V, you can see it as the power series in X, where here you have a shift. So K of Xn is seen as the dual of the KT minus n minus 1. So you have this shift. So this shift is used because then when you work with the vertex algebra, the mode of degree n, you want it to be the power of minus n minus 1. So to respect this shift, we use the shift here. And this is an equality of G module, so the degree here is the same. So one subtlety here is that K of tt minus 1 is an algebra with a usual product. So if you when I say usual product, is you take the tensor product of spaces, because this KTN, you see it's a gamma graded vector space. So if you take tensor product for this KTN, you can do what you would expect, just add the powers of t. But it will not work inside this space. So this Vx minus 1 is not an algebra with just the usual tensor product. And this is because the degree of x to the n is not n times the degree of x. This is due to this shift with n minus 1. So you can define a kind of shifted product to get back this type of product where you add the degrees, but you need a shift. It's not the usual one. And in particular, and something that has important consequence later on, is that the degree of x minus 1 is 0. And it's not just minus the degree of x. And this will have then kind of important ramifications in the third section. I will talk about more later on. So now that we have this loop algebra and this x, we can go to the continuous function, and which it is the last of the ingredient we need to define our spaces. So you can consider a topology on this ktt minus 1, where the open set are just the kt times t to the n. And this, you have open set, you have inclusion when n increases as an integer. And then if you have topology, you can look at the continuous function between your space and your topology. So here, the V will be seen as the pointwise topology. So each element is an open set in itself. And there will be two important types of continuous functions. So notice here is kind of just a generalized notation because we don't know in which type of morphism we want to look at. But the first part will be the continuous G-gamma homomorphism. So it will be the G-gamma homomorphism between the loop algebra and V, where f to t to the n becomes 0 when n is big enough. And the second important continuous function will be the internal home space continuous function. So it will be a subset of the home space. And these will be given by these homomorphisms. So notice that this is very general because you don't look at the degree at all. You can do anything you want with the degree. It just needs to be homogeneous. But here, you have a sum regarding each component. So it's not exactly the same structure. But you still need the same condition, so the kind of duality, the continuous condition. And this, I'm sure we will go to, as you'd expect, the truncation condition for vertex algebra. So this will be the two important home spaces, so G-gamma continuous and the internal home continuous functions. And yes, so as you would expect, this internal home, because the generalized internal home gave the power series that we had here. If you look at the continuous, it will correspond to the truncated Laurent series. So you can have infinitely, the power of x can be infinitely high, but if you go below 0, it will need to be truncated at some point. So this is for the setting. So now we have all the ingredients we need to define the main object of this talk. So we will consider, again, gamma, this abelian group. It will be noted with a plus, the addition convention. And we take beta to be just a map between sets of gamma times gamma and then k. And if you have two elements u and v inside your category G-gamma module, we define this map T to the beta, which is kind of your braiding, but you modify it by the beta. And so you go from UV to VU, and so you switch the order, but in front of it, you have this beta that appears that is given using the degree of U and the degree of V. So again, this notation with the bar is the degree coming from the gamma gradation because it's G-gamma module. And so you can define this on all homogeneous components, and then by linearity, you extend to everything. And just to fix notation, because we will need some relations on beta afterwards, the first relation we will need is possible relation that beta is satisfies is this one. So beta doesn't change if you change the sign of the two variables, so gamma 1, gamma 2 minus gamma 1 minus gamma 2. And the second condition is linearity in the second variable. So not the first one, it's just the second variable. So this, we don't assume for now that beta satisfies this, but afterwards we will need the relation will appear, and so I will say relation 1 and relation 2. This is just to set the stage. And so now I can give the definition. And so we call G gamma beta gamma 0 vertex algebra. So later on I will just say vertex algebra, but remember that this will always be attached to it. Over the field K is going to be a G gamma module V, so a gamma graded vector space, with a map Y of X, which is like this. So it's a map from V times V to this internal Hom space, and it needs to be a map of G gamma module. So it needs to preserve the gamma gradation. And here, the KTT minus 1, so the T is of degree gamma 0. So this is the gamma 0 you have here. So it defines your loop algebra. And so you can write it more explicitly as a map, so from V times V to the power series, using the identification we did before between this one and V. And we have, again, the same type of shift between the mode n and the power minus n minus 1. And we want a vacuum, so an element in V0, where we have different axioms satisfied. So the first one is just the vacuum. So it's just that the vacuum will kind of act as the identity. Then we have the creation. So if you apply on the second variable, you just have power series in X and no negative power. And the first component is just V itself. Then we have a truncation condition. So this truncation is expressed using the restricted dual. So more specifically, if you have an element in the dual and two elements in V, you can apply U prime to this power series. So you apply it term by term on each coefficient of power of X. And you want this to be in the curly Hom, continuous curly Hom of this space. Then you have a version of the Jacobi identity. So this is the Jacobi identity you are used to, expressed a bit differently, where here the important part is that here you have a twist, not just you change the order, but you change the order by this T beta. So the twist modified by beta. And finally, you have some derivation properties. So you have, if you take D to be this residue, so it's indeed a map from V to V, you want these two properties satisfied. So a property where if you kind of commute D and Y, it's the same as the derivative of Y. And if you apply Y to an image of D, it's also the same as this derivation by Y. So notice in the name, so G gamma means that we work with gamma graded spaces. This beta is because the Jacobi identity is twisted using the beta. And the gamma 0, it means that the loop algebra, the gradation you start with is gamma 0. So that's all the elements of this name, G gamma beta gamma 0 vertex algebra. So these 5 components are the definition of this vertex algebra. So a small remark is that if gamma is just 0, so trivial group, the truncation condition is equivalent to the usual one, where the mode becomes 0 when n is big enough. Another one is that if beta is just 1 and basically just doesn't do anything, it just gives you the constant 1, the axioms 1 to 4 through 4 are equivalent to the usual definition of vertex algebra. So then you can think of this definition as a type of deformation using the twist by beta of the usual structure of a vertex algebra. Then if another remark is that if beta is just 0, meaning that in the Jacobi identity, this map will be 0. So all this term, so sorry, the term on the right here will just disappear. If it is the case, then we can, from what remains of the Jacobi identity, it leads to the associativity axiom of what's called a field algebra with n equals 0. So you can think of a field algebra as a vertex algebra where you do not have the commutativity condition on the vertex operator. So it's a type of more general vertex algebra. And also from the Jacobi identity, we can go to the defining relation of what's called an open string vertex algebra, which is a type of similar construction, but you can think of it as some kind of vertex operator algebra without the commutativity condition. So you don't necessarily need the whole conformal element, but you need kind of L-1 and L0 because you will need eigenspace decomposition. But the important point is that this definition, through this deformation, kind of relates the usual vertex algebra, the field algebra, and the open string vertex algebra. And finally, the axiom 5, so the derivation condition, it is needed because the translation operator plays an important role for vertex algebras. And here, for this type of definition, it's not a consequence of the other axiom when beta is completely general. So for usual vertex algebra, this is just the -2 mode applied to the vacuum, and these are just consequence of the Jacobi identity. Here, it will be true for some betas when it satisfies some special relation, but not in all generality. So because it's an important structure to have, we've added the axiom so that we know it's always true and not just a consequence. And so, as I mentioned before, we have a duality between algebra and coalgebra. And if you start from an algebra and you want to define what is a coalgebra, you take all the commutative diagram that define your structure for an algebra, so the morphism and the unit, and you just reverse all the arrows in the diagrams, and this gives you the co-product and the co-unit for your vertex algebra, for your coalgebra, sorry. And so here we can basically do the same thing, is that a vertex algebra, you can think of it as a space, so vector space, and instead of having just one product as an algebra, you have these infinitely many products yn, and the unit, which is, so the vacuum, which is an element in V0, you can think of it as a morphism from K to V of degree 0. So this will be also a J-gamma homomorphism. So it preserves and it's of degree 0. And so all the structures that we defined in the previous proposition, you can create commutative diagrams for all of them. And then you just reverse the orientation. And that's what you choose as the vertex coalgebra. And so if you do and you write everything and you inverse all the arrows, you will get the definitions of a vertex coalgebra, again with this epithet in the front. And so it will be a map from this lambda. So this is just a y inverted, but I will call it lambda, so lambda x. So it's a map from V to the internal home between the loop algebra and V times V, where again T is of degree gamma 0. So you can write it as a map like this. And you will get epsilon, so the co-vacuum, instead of being a map as the vacuum was a map from K to V, this will be a map from V to K. And you will get all the dual version of the previous axioms. So you will get the co-vacuum, So you basically all the commutation, you switch the order, and all the tensor product, you permute everything. So you get a co-vacuum condition, you get a co-creation condition. So here you have, here is for the identity times epsilon, and this one is for epsilon times the identity. Then you get a version of the truncation. So again, with the continuous of the internal hum. You get a co-Jacobi identity. So same type of identity and still a twist by beta. And then you also impose a derivation property. So this is the reverse. So you switch the direction of D. And you again can define through the residue a map from V to V. And you want this type of identity to be satisfied. So if you compare them side by side, it's really you reverse everything. So once you have done that, so you have your vertex algebra and you have the dual counterpart, vertex coalgebra. So you might already be familiar with a different notion of vertex operator coalgebra, which was introduced by Hubbard. And our definition is slightly different for the following reasons. The first one is that the choice of the pairing with the dual space is not the same. So we have this twist that will kind of change the order when you go to the dual and when you dualize again. And so it introduces different, so the convention leads to different results. And the reason we choose this convention is that it makes more sense when you work in monoidal categories to have this twist, because when you work with so then rigid category or categories where you have some type of duality, the dual naturally introduce a permutation through the braiding. And so we use this to start working in a more general setting. The next point is that we do not consider any conformal structure on V. So there's no conformal and co-conformal vector on V, as it was the case for Hubbard. So it was vertex operator coalgebra. Here is just vertex coalgebra. There's no conformal structure. And another point is that in the definition of vertex operator coalgebra, when you look at the series you get through the vertex operator, you have a singularity at 0 when you work with the vertex algebra. And when Hubbard gave the dual version, the singularity at 0 was sent to infinity. And so the truncation condition you had for vertex algebra, where you wanted the mode to be 0 when n is big enough, now became a truncation where the mode needs to be 0 when n is small enough. And so you change the order. And here, the singularity stays at the same point. So it's just the mode that will shift around, but the singularity will stay at the same point. And this is because this singularity is kind of controlled through the loop algebra. And here the loop algebra does not change. If you notice in the definition, we switch basically V and V times V around in the definition, but this just stays put. And because of that, the truncation condition, you don't change the direction in which you apply the truncation. And so, as you would expect, we have, so vertex algebra, we can define a type of modules. And so using the previous definition, we can define, so left vertex algebra module, so you have an action on the left side, and also right vertex algebra comodule, where you apply on the other side. And so the first result I will present is that you take your gamma any abelian group, you take beta to be, again, your map of sets. And then you want beta to satisfy the relation 1. So this relation 1, remember, it was this one. So beta needs to be invariant by this minus. You change the signs and it doesn't change the value of beta. So if it satisfies this, then the restricted dual prime gives you a bijection between the Harishchandra vertex algebra and the Harishchandra vertex coalgebra. So remember, Harishchandra, it means that all the homogeneous components are finite dimensional. You can have infinitely many of them, but if you take just one, it needs to be finite dimensional. And so this is true for vertex algebra. So this is a bijection from both sides. So you can go in one direction or the other. So nothing kind of is excluded. If you have one, it comes from another one, and you can do the correspondence. And you have the same type of relation, but for the modules. So the first part is the same. You take gamma and beta. You assume that beta satisfies this invariance. And then you take V. So you start with V Harishchandra. Everything is finite dimensional. And then the dual gives you a restriction between the left V module, who still have this condition of finite dimensional on each component, and then the right V prime comodule. So these are modules for a vertex algebra, and these are comodules for the vertex coalgebra V prime. And you have this correspondence between the two. So this is for the vertex algebra, vertex coalgebra, and the duality between the two. So this is kind of half my title, which was the duality. The other half was about this C2 algebra, C2 coalgebra. So now, what I mean by C2 coalgebra. So first, here we need some type of definitions, because we have this beta that kind of changes the notations. So we say a G gamma algebra. So it's a triple. So this is pi. It's the var pi in tech, but I don't know why it looks like this, but it is a pi for a product. And one, where this is a G gamma module, gamma graded vector space. This is a product, and this is a unit. All these maps need to be homogeneous, so you preserve the degree. There's no shift in degrees. And you need two conditions, one associativity and one unit. And finally, we say that an algebra is beta commutative if the product is invariant by the twist by beta. So it's a type of commutativity relation, but you still have this beta that appears in front of it. So this is a G gamma algebra. Then we have, yes, we need one more notation, is that if you have a G gamma module and your map beta, we define this permutation, so psi of beta, between the tensor product of V by itself 3 times and the same space. And this corresponds to the cyclic permutation that you have in, for example, Lie algebras, where you have ABC and it becomes BCE. So this is the same, but again, you have this beta that will appear in front of it. So it's the kind of beta deformation, let's say, of the usual cyclic permutation. And then we can define a G gamma beta Lie algebra of degree gamma. So this, it will be a tuple, so L and pi 0, where L is going to be a G module. So we don't look at field of characteristic 2. This is for the skew symmetry, because otherwise we need to give another one, and it's not as simple to compute with it. So for the sake of simplicity, we'll just exclude field of characteristic 2. And then P0, it's a linear map of degree gamma. So here we don't need homogeneous, we need degree gamma, such that you need the skew symmetry, which is the usual you have for Lie algebra. And then you have a Jacobi identity, but instead of just the usual cyclic permutation, you have this psi beta that plays the role of the cyclic permutation. And then finally, the last definition we need is if you have algebra, you have Lie algebra. When you combine, you have the Poisson structure. And so our version, let's say in this context of the Poisson algebra, so Poisson algebra of degree gamma, will be a tuple, so you will get A, pi 1, and pi 0, where A1 pi will be just a G gamma algebra, so homogeneous product, homogeneous identity. Then A pi 0 will be a Lie algebra of degree gamma. So through this pi 0, you will have this structure. And then you have a compatibility condition between the two. So the product pi and the product and the, let's say, Lie bracket pi 0 needs to satisfy this relation. So here, if you take gamma, for example, equals 0, so if you take gamma equals 0, all of these are just the usual definition of algebra, Lie algebra, and Poisson algebra. So this is just a kind of generalization to, let's say, bigger spaces of those familiar notions. So now for the C2 notions. So if you have a vertex algebra, we can define so the space C2V to be just the image of the -2 mode coming from the vertex operator. And then we can consider the space of RV, which is the co-kernel of the -2 mode. And of course, we can show that this is the same as just the quotient of V by C2V. And so we know in the classical setting that this is a Poisson algebra through the -1 and the 0 mode. And here we can play the same game. You can use the -1 and the 0 mode to show that they will induce homogeneous linear maps, so pi and pi 0, between RV, so the tensor product of RV with itself, and RV. And the vacuum map, so the vacuum vector, which was, you can see it as a map from K to V, so homogeneous map from K to V because K is centered in 0. If you compose that with the projection from V to RV, so this quotient, it will give you a linear map, so we call it 1 of RV, from K to RV, is just the composition of the two maps. And so with this notation, this construction, we can prove that starting from a vertex algebra, and then we assume that beta satisfies relation 2. So remember, relation 2 was this one. So you need linearity on the second component. If you have this condition 2, sorry, I didn't go to the right one. Then, so the tuple formed by RV, the product pi coming from -1, the identity coming from the vacuum, and pi 0 coming from Y0, will be a Poisson algebra of degree 0, and it will also be beta commutative. So you will have this type of Poisson structure. The Lie bracket will be of degree 0. It will be, in fact, homogeneous. And everything will be, so the product, pi, will be beta commutative. So we'll have this invariance through beta. So this relation 2 is important, not for the algebra side, because the algebra side always works. But if you want the Lie algebra structure, you need the condition 2. And this is due to this cyclic permutation. It creates a constraint that in order for it to be satisfied, beta needs, let's say, previous conditions already satisfied, and these are the condition 2. So now we have so in the classical case, we have the Poisson structure, and here we have, let's say, a deformed Poisson structure by this beta over the gamma-graded vector spaces. So the part that we didn't expect at first was that the degree will become 0. And the fact that the degree is 0 is due to the, when we go before and I introduce the loop algebra and X, we see that the way we shift the degree between T and X with this -n -1, it makes it so that the degree of X -1 is 0. And because of this degree is 0, the avalanche effect is that in the end, the map becomes homogeneous. So because of this shift in degree between T and X, you get in the end that the map becomes homogeneous. So now if we go to the C2 version of it. So you can look at all the definitions, so 3.1, 3.2, and 3.3 of algebra, Lie algebra, and Poisson algebra. All the conditions, for example, here and here, these correspond to just commutative diagrams given by the maps T beta and omega 0. This is also a commutative diagram. And so if you write the commutative diagram and you commute all the arrows, you can define the G gamma coalgebra, G gamma beta Lie coalgebra, and the co-Poisson coalgebra version of the previous proposition. And so now we have these definitions. The space we consider is if you start with a coalgebra V, we look at the space, so RV, so the R, which again, you switch the notation, and you look at the kernel of the -2 mode for the co-structure. So if you do that, then you can look at the -1 mode and the 0 mode. They will also induce a homogeneous linear map, but now, of course, the order of the maps will change, and it will send RV to the tensor with itself. And then you have, because V is a vertex coalgebra, you have a map epsilon, so it's the co-vacuum. It's a map from V to the field. And so if you restrict epsilon to this RV, because here RV is really a subspace, it's not a quotient, it's a subspace. So you take the restriction of epsilon and you obtain a map like this that we call C of RV. And so you have your RV space is well defined, you have delta and delta 0, and you have this C of RV. And so if you take such a V, and again, you assume that beta satisfies the relation 2, so it's linear on the second variable, then the tuple formed by RV delta C of RV and delta 0 is going to be a co-Poisson coalgebra of degree 0. So you have product, so co-product, Lie co-bracket, and a compatibility relation. It's of degree 0 because everything, the Lie co-bracket is homogeneous, and the coalgebra product is going to be beta co-commutative. So everything is preserved by this twist by beta. And so now you have vertex algebra with the RV and the Poisson structure. You have on the other side vertex coalgebra, and you have this other RV which gives you a co-Poisson structure. And we know that if you look at the vertex algebra realm, you have a duality on the Harish-Chandra part. And now we go down to the RV. So how do you bridge the gap, and is there a bridge? And so we can, in fact, bridge between the two. And so if you start with V, a Harish-Chandra vertex algebra, and you assume that beta satisfies relation 1 and 2, so you need relation 1 so that you can say that V prime is going to be a vertex coalgebra. And you need relation 2 because you want RV to be a Poisson algebra. So that's why you need these two components. If you remove one or the other, then everything falls down. So these are the basic requirements. Then you will have an isomorphism of Poisson algebra of degree 0, so everything is homogeneous, between RV and so the dual of the coalgebra, so the C2 coalgebra of the dual of V. And so basically, if you take the double dual, then you change what co-structure you look at. And so this is true if you start with a vertex algebra, but you could say, if I don't have a vertex algebra, but I have a coalgebra, then you could play the same game. So you start with Harish-Chandra vertex coalgebra. You still need the assumption that each homogeneous component is finite dimensional. You assume that beta satisfies your two relations so that you can then go from vertex coalgebra to vertex algebra. And also you have a nice co-Poisson structure on your C2 coalgebra. Then you will get an isomorphism, so of co-Poisson coalgebra of degree 0 between your C2 coalgebra and the dual of the C2 algebra of the dual vertex algebra. And so, yes, didn't forget the sentence. So this is true for the algebra, but as I mentioned, you can work also on the modules. And so if you have, for example, a vertex algebra V, you have a module M, you can look at the co-kernel of the -2 mode for this module. Through that, you can define a C2 module, sorry, Rm, and then likewise, you can define a C2 co-module for the C2 coalgebra, and you can play the same game, and you will have similar results. But instead of V here, you will have a Harishchandra module, and the isomorphism will be isomorphism of Poisson algebra module or co-Poisson coalgebra co-module. But the same thing will be true for the module. And in this respect, if you look at the results for the module and you specified the module to be the adjoint module or the adjoint co-module, you will get back those results. It will kind of fit on the same thing. So everything is true also for the modules. So this gives you kind of a scenery of this vertex algebra, vertex coalgebra, and then when you go down to the core structure, you have this nice kind of Poisson beta deformed Poisson algebra, co-Poisson algebra. And so what are the perspectives for this structure? So the first one is that here we look at the duality, so from V to V prime, where we look at the dual on each. So we cannot look at the dual of the whole space, so as a map from V to the field, because as I mentioned in the introduction, this may not be a gamma-graded space. So we look at the restricted dual, but there is another way to look at the notion of duality through what's called contramodule. So instead of looking at the map from V to the field, you look, if you have a space M for coalgebra, a contramodule for the coalgebra is space M where you have such a map. So you have morphism from V to M, and this is a map to M. So this is defined for coalgebra. So imagine if V is a coalgebra and M then becomes a contramodule for the coalgebra. We want to see what happens if instead of a coalgebra, you have the vertex coalgebra, so you have much more involved structure on it, and how will it relate to this duality with vertex algebra. So we know if you have a module for a vertex algebra, its restricted dual will give you a module, so co-module for the vertex coalgebra. But then how does this one relate to the contramodule for this vertex coalgebra? This we don't know yet. Another one is to construct examples of vertex coalgebra that do not come from algebras. So when it's Harishchandra, we saw that we have a bijection between the two, and every vertex coalgebra comes from another one. But as I mentioned before, if you look, for example, at algebras, and the categories are not rigid, if you have a coalgebra, you take the dual, you always get an algebra, but it's not true in the other direction. And so you might have coalgebra who do not come from algebra. And so what happens for in the vertex case, how can we construct vertex algebra directly without relying on this duality to begin with? And then, so when you work with vertex algebras, you usually, have two algebras to contend with, the C2 algebra, which is Poisson, and the dual algebra, which is going to be a filtered algebra. And what would be the let's say, co-version of the dual algebra? And for now, it's not clear. because the way the GeoAlgebra is defined through this circle product, which define the space OV by which we quotient to get the GeoAlgebra. It does not work. It doesn't kind of preserves the filtration well enough to make it obvious how to dualize this version. So when you work with the C2 algebra, the C2 space, everything is nicely homogeneous. Each component is homogeneous. So you kind of see how you go from one to the other. But because of this product is much more involved, it's not completely clear how to define a Geo coalgebra for a vertex coalgebra. So this is still an ongoing investigation. We still do not have a satisfying answer for this one. And so thank you for your attention. And if you have any questions, feel free to ask. Thank you.